This is going to be a video about Chapter 17, Phases and Phase Changes. Okay, the first thing we're going to talk about is an ideal gas. And for an ideal gas, the interactions between the molecules can be ignored. So that means we're going to assume that there's no attractive or repulsive forces between those molecules. And if there's an increase in temperature, that's going to result in a higher pressure because the particles are going to be moving faster, crashing into each other more often, therefore creating a higher pressure. And that's if the volume and the number of particles is constant. Now, the more molecules that we have in there of a gas, then that means they're going to hit each other more often because there's going to be more of them, and that will again result in a higher pressure. And that's as long as our temperature and our volume is constant. And if we increase the volume, that means they're going to have more space to move, so they're going to run into each other less often, so the pressure will decrease. And that's if temperature and the number of particles is constant. So we can take all those relationships and we can put them together in one. We said that as the number of molecules increased, the pressure would increase. As the temperature increases, the pressure would increase. And as the volume increased, the pressure would decrease. So we could put those all together, and K is going to be some kind of a constant of proportionality. And that constant is called the Boltzmann constant. And the Boltzmann constant is 1.38 times 10 to the negative 23rd joules per Kelvin. And you're going to be using this constant in some of your problems. Now, if we talk about the ideal gas law, we can take that constant of proportionality and we can rewrite this equation to be PV equals nRT. That's the ideal gas law. P is our pressure, V is our volume, N is the number of moles that we have, R is the ideal gas law constant, which is 8.314 joules per mole Kelvin, and T is going to be our temperature. So instead of number of molecules, like we had in our last one with the Boltzmann constant, we're going to use number of moles. So here I have a problem, and I have a sample of gas that's at 310 Kelvin, that's my temperature, has a pressure of 101 kilopascals, and I want to know the volume of 1.25 moles, if the gas is ideal. So I'm going to be using my ideal gas law, which is PV equals nRT. It says my pressure is 101 kilopascals. I'm going to need this in pascals, so I'm going to multiply this by 1,000. I want to know the volume. I have 1.25 moles of a gas. I'm going to use my ideal gas law constant, 8.314, and my temperature is 310 Kelvin. So I'm going to be taking everything on this side and multiplying it together, and then dividing by my pressure, and I'm going to get a volume of 0.032 meters cubed. So the pressure we're going to have in pascals, volume is going to be in meters cubed, N is your number of moles, R is always that constant, and temperature has to be in Kelvin. Okay, we said N is the number of moles, and the number of particles in a mole is called Avogadro's number. And Avogadro's number is 6.022 times 10 to the 23rd. That's how many molecules are in a mole. Kind of like 12 is how many dozen that we have, how many things in a dozen. So N, the number of moles of a gas, if we want to find N, or if we want to find the number of molecules, in this case, if I want to find the number of moles of gas, then I'm going to have to take my number of molecules, which is N, and divide by Avogadro's number, which is 6.022 times 10 to the 23rd. And that would tell me how many moles that I had. Or, conversely, if I have this equation, if I take the number of moles that I have times Avogadro's number, that's going to tell me the number of molecules that I had. Now, the molecular mass, or the molar mass, is the mass in grams of 1 mole of a substance. And this we can get from the periodic table. So if I would look for helium, molar mass is 4.0026 grams per mole, or copper would be 63.546. So this is just the mass that we can find off the periodic table. And if I want to find the mass of an atom, I take the atomic mass and I divide by Avogadro's number. Okay, now we're going to look at some different relationships. So Boyle's law says that the pressure varies inversely with the volume. And that means that if I take the pressure times the volume now, that should equal the pressure times the volume later, as long as my number of molecules and my temperature stays constant. This particular picture shows isotherms, and these are curves that we have at a constant temperature because we said that our temperature has to remain fixed. And we can see that there's an inverse relationship between volume and pressure. Charles's law relates the volume of a gas with the temperature, and we can see that as the temperature increases, so does the volume. So in that case, V1 over T1 is going to be equal to velocity final, or volume final, over temperature final. And that's as long as my pressure and my number of molecules stays constant. Now I can put both of those relationships together into one. That's called the combined gas law, where pressure times volume, that's Boyle's part, over volume divided by temperature, that's Charles's part. If I put those together, then I can see that I have this relationship. So pressure P1 V1 over T1 now is going to be equal to P2 V2 over T2 later. And any variable that's constant can be left out. For example, if my temperature is constant, then I can cross out my temperatures and I can see that P1 times V1 equals P2 times V2. And that was Boyle's law. Or if my pressure is constant, I would get rid of the pressure and I'd have V1 over T1 is equal to V2 over T2. And that was Charles's law. And last chapter, we had P1 over T1 is equal to P2 over T2. That would be if my volume is constant. So this one equation is going to work for all three of those instances. So here I have an example using the combined gas law. It says I have 24 milliliters of a gas at 32 degrees Celsius and a pressure of 0.9. I'm going to heat it to 57. The volume expands to 36 and they want another new pressure. So I'm going to use the P1 V1 over T1 is equal to P2 V2 over T2. And just so you notice, the ideal gas law problem on your assignment and 17.10 are both going to be dealing with this combined gas law. So in this case, my pressure is 0.9, my volume is 24, and my temperature is going to be 32, but I have to have this in Kelvin. So I'm going to take 32 plus my 273 and get 305. They want to know what the pressure is going to be later. My volume expands to 36, and my temperature goes to 57, so I'm going to have to take 57 plus 273 to put it in Kelvin, which is 330, and those temperatures always have to be in Kelvin. It doesn't matter what my volume units are as long as they're the same, and same thing for the pressures, it doesn't matter what those are as long as they're the same. So to find P2, I'm going to take 0.9 times 24 times the 330, I'm going to be dividing by the 305 times the 36. And when I do that, I'm going to get 0.6 atmospheres because it's going to have the same label as my pressure did for the first case. And I have one significant figure because 0.9 only had one. So one thing to remember, temperatures have to be in Kelvin, otherwise this won't work. And that's the case for any of those relationships. If pressure is constant, anytime you have temperature, it's going to have to be in Kelvin. Now in this case, I have a balloon. They're showing you a picture that was inflated at room temperature and then it was cooled with liquid nitrogen and the volume decreased. And we can see that because it's all wrinkled up. So as temperature got smaller, so did the volume. Now, the kinetic molecular theory says that gases consist of large numbers of molecules. Those molecules are always moving, and they obey Newton's laws. Collisions with other molecules and with the walls are elastic, which means if they hit something, they're going to bounce back off at the same speed. And the pressure is always proportional to the average kinetic energy of the particles. And we know that pressure is a result of the collision between the molecules, and that's when we were relating all of those number of molecules and temperature, all of that to pressure, and that's because of the number of collisions. And it depends on the mass and the speed of the molecules as well as the container size. So the volume, the number of molecules, and how fast they're moving. Not all molecules are going to have the same speed at the same temperature. The speeds are going to be represented by what's called the Maxwell distribution, and it depends on the temperature and the masses of the molecules. I can see here that in this case, this is the bulk of them have this speed, where at 1100 Kelvin I can see that the average speed is much greater. So the higher the temperature, the average speed is higher, but this is a distribution of all of the speeds of the molecules. Now, because those are moving at different velocities and it has to do with the mass, we could figure out the kinetic energy. And the average kinetic energy I know is 1/2 mv squared. Or I could relate that in terms of my Boltzmann constant and my temperature, which would be 3/2 times K, the Boltzmann's constant, times my temperature in Kelvin. And this is going to be related to 17.24 on your assignment. Now, if we want to find the average, meaning the mean velocity of those particles, it's called the root mean square velocity. And the velocity, root mean square, is the square root of 3 times r times t divided by the molar mass. So 3 is a number, r is going to be your ideal gas law constant, which is this 8.314. T is your temperature in Kelvin, and mm is your molar mass. It has to be in kilograms per mole, not grams per mole. And that velocity is going to be in meters per second. So here's going to be an example, and they want me to find the root mean square speed. So I'm going to take 3 times r times t divided by the molar mass, and I'm going to have to square all of that. So 3r is my ideal gas law constant. T is my temperature in Kelvin, so 0 plus 273. Okay, I'm going to have to find my molar mass for NH3. So nitrogen is 14.0067. 3 hydrogens, 1.0079 from the periodic table. And if I add that up, I get 17.0304, which means that my molar mass is in kilograms, 0.017304, and then I have to take the square root of all of this. And I get 632 meters per second. Okay, so the root mean square speed is slightly greater than the most probable speed and the average speed. So we can see here's the most probable speed, here's the average speed, and the root mean square speed is slightly higher than that. And that's what we were just finding. The average kinetic energy, and we're going to look more at the kinetic theory, we can relate to the internal energy. And the internal energy is the sum of all of the kinetic energies of the molecules. And in this case, the total internal energy would be 3/2 times n times k times t. 3/2 is a number, n is the number of molecules, k is that Boltzmann's constant from the first slide, and t is your temperature in Kelvin. And since it's energy, it's going to be measured in joules. Now we're going to look at stress and strain. Solids have definite shapes, but they can be stretched or deformed. So in this case, we can see we have individual molecules. If we had a certain length, we could extend that length if we applied a force. and this directly relates to elongation of springs and Hooke's laws. So the amount of stretching depends on the force that we would apply, and if you remember back from our previous chapter, that according to Hooke's law, the amount of force and the amount of stretch are proportional. So we're going to expand this relationship when we talk about elastic deformation. So Y is this Young's modulus, and there's a table here for different materials and their Young's modulus. And this depends on the material. And problem 17.38 is going to be using this equation. F is my force, Y is my Young's modulus, which I would have to look up on a table. Delta L would be the change in the length. L0 is the original length, and A is going to be your area. And remember, for solids that are just, nice square solids, area is going to be length times width. If we're dealing with circles, then our area is going to be pi r squared. Now, shear deformation is when we have opposite sides of the object and they're pulled in opposite directions, meaning this side of the book is pulled this way and this one is pulled this way. And we can see that this is stretched. So it was here and then it's gone this way. And this is the original length. And A is the area of the cup. So in this case, our deformation is still proportional to the force, but I'm going to use what's called the shear modulus. So F is still my force, going to be in newtons. S is my shear modulus. Delta X is going to be the amount that it was deformed. L0 is the original length, and A is my area. So this is very much like the last one that we had with Young's modulus right here, and this was the change in the length. So it's the same kind of equation, except we're using the shear modulus instead of Young's modulus. In this case, I'm going to be measuring that shear strength, and I have a 22 kilogram chimp, and it's hanging from the edge of a branch. So I have a branch here, and then I have my chimp that's hanging on that branch. And the branch has a diameter of 4.6. The end of the branch is going to sag with the weight of the chimp. So by the time the chimp hangs on this, it's going to stretch. And it says it sags with a weight of the chimp by 13 centimeters. And I want to know the shear modulus for this branch. So according to my last equation, I have F is equal to the shear modulus, delta X, amount that it's changing, over the original length times the area. So my force is going to be the weight of this chimp. So weight is M times G. And mass is 22 kilograms, and I'm going to take this times 9.8. And that's going to be my force. And that's going to be 215.6 newtons. I'm trying to find the shear modulus. And it says that this is sagging, so that's the amount of my change, of 13 centimeters, which is going to be 0.13 meters. And the original branch is 1.1 meters long. Now I'm going to have to find the area of this branch, and it's going to be a circle. And it's going to have a diameter of 4.6, which means my radius is going to be 2.3 centimeters. Or this is going to be 0.023 meters. And to find my area, I'm going to have to do pi times r squared. So pi times 0.023 squared. And if I multiply that, I'm going to get 0.00166. So I'm going to divide those two, take it times this, and then take my 215.6 divided by all that stuff. And I'm going to find my shear modulus, which is 1.1 times 10 to the 6th newtons per meter squared. And that's going to have two significant figures because everything else had two. Alright, if a solid is compressed, it's going to shrink. So in this case, I'm going to use beta, which is called the bulk modulus, and it's going to shrink in all directions. That's why we're using volumes. So the change in the pressure is going to be the bulk modulus, the change in the volume, and V0. And you're going to have a problem on your assignment where I think it's taking a copper ball and it's going to be way down in the depths of the ocean, and they're going to ask you to find, I think, the bulk modulus or the change in volume, one or the other. So the change in pressure is going to be how much it changes from atmospheric pressure. And remember, atmospheric pressure is 1.01 times 10 to the 5th pascals. And this change is going to be whatever the pressure is later minus this. So my change in pressure is going to be the P later minus the P0. This is going to be your bulk modulus for your type of material that you're going to put in here. This is going to be the change in volume, and this would be the original volume. And if we're talking about spheres, the volume of a sphere is 4/3 pi times r cubed. And that's going to have to be in meters when you plug it in here, because if you'll notice, these are in meters squared. So pi times r cubed. So radius is going to be in meters, and this is going to be how you're going to find the volume of a sphere for your original volume. Okay, so we said stress is the amount of force that we're going to apply. The strain is the resulting deformation. And stress and strain are proportional to one another. And that's just like our F equals kx. So the stress is the force, and this is the amount that it moves. So this would be like your force and your x. And in this case, we said that the slope was k, which is our Hooke's law constant. So this is just like when we're dealing with springs. So we can see this is proportional up to a certain point. In fact, it's linear. But then when that stress becomes too large, we're going to have permanent deformation occurring, which is that bending. Moving on, we have phase, equilibrium, and evaporation. And when we are at equilibrium, then the rate of evaporation, number of molecules that are escaping, is equal to the rate of condensation, the number that are falling back in. So the amount that's evaporating and the amount that's settling back down are the same at equilibrium. The equilibrium vapor pressure is the pressure of the gas that's in equilibrium with the liquid. So when they're at equilibrium, the pressure, and it depends on the temperature. The higher the temperature we can see, then the result vapor pressure is going to be higher. And the normal boiling point of a fluid is going to be exerted at atmospheric pressure. Now we look at our curves. We have a vaporization curve. This determines the boiling point of a liquid. And the liquid boils when the vapor pressure equals the external pressure. Usually that's atmospheric pressure. So that means the pressure is going to boil at a lower temperature if I have a lower pressure. And that's going to be why liquids are going to boil at a lower temperature when we have higher altitudes, because we have a lower pressure. Now this is a phase change diagram, and you're going to have two problems that are looking at phase change diagrams. One is 17.52 and the other one is about ammonia. And this is a phase change diagram, and you can see that we have solid, liquid, gas, always in that order from left to right. And the transition here between a solid and a liquid is where we're going to have melting occur, that fusion curve. And the boundary between solid and gas is my sublimation curve. And between a liquid and gas is going to be when things are going to vaporize, and that's going to be my vapor pressure curve. And the critical point is this point, and that's the point that there's no longer any difference. We can't tell the difference between a liquid and a gas. We say that there's only a fluid. And this point where all three phases meet is called the triple point. There's three phases, so it's called the triple point. So we said that that fusion curve was the boundary between a solid and a liquid, and A is the fusion curve for most materials, and this is the fusion curve for water, so we can see it kind of points the other direction. The sublimation curve is the boundary, we said, between the solid and the gas, where things are going to sublime, and where all those three phases meet, that's going to be the triple point. And in this particular diagram, we can see that the triple point is right here, and we could read the resulting pressure that would be. Now in this case, this is my my vaporization curve between a liquid and a gas, and then I can see if I wanted to read at 101 kilopascals what that temperature would be. So I could read things off this graph. So this is going to be where you're going to have vaporization. This is going to be my sublimation, and this is where things are going to be melting, your fusion curve. And we could read certain temperatures and certain pressures along that curve. Likewise, if they gave me a certain temperature and a certain pressure, I could find out what state of matter it is. So they gave me a temperature here and a pressure here, then I could see that I was in the solid phase. And so in those two questions, we're going to be looking at these phase change diagrams. Now, in a closed container, it's going to reach equilibrium, where the amount of evaporation and the amount of condensation are going to be the same. But in an open container, it doesn't reach equilibrium because it continues to vaporize. And the high energy particles are the ones that are going to vaporize, leaving behind those with less energy. And because they have less energy, they're going to be cooler. And that's exactly why we sweat. Those high energy particles leave, resulting us with less energy and therefore cooling the liquid. And not just molecules at 100 degrees will escape, which is the normal boiling point. Evaporation can cause a planet to lose its atmosphere, because some of the molecules will have speeds that exceed the escape velocity. So that means at any temperature these things can escape. It just depends upon what their speed is. And evaporation occurs faster for lighter molecules and for less massive planets. And here I can see for oxygen, this is the relative probability at a certain speed, how many particles will have that ability. And for hydrogen, that I can see that this is at a much higher temperature. So it depends on what the masses are for those molecules. Now when two phases exist, the temperature remains the same. So in this case, I have an example here that shows that I'm melting something. So I have ice. First thing that happens is I could bring ice from whatever my temperature is up to 0. So that's where I'm going to be changing temperature. Once I get to where I have ice and liquid together, that's two phases coexisting, that temperature is going to remain the same the whole time that it's melting. And that's because the heat goes into changing the phase of the material. Now, once it's all water, then I can increase the temperature of water again up to 100 degrees. At 100 degrees, it's going to start to change phase. So in that case, the temperature is going to stay constant because I have two phases of matter again. And once I have all of that changed over to steam, then I can increase the temperature again. Now, any time that I am changing temperature, so this section, and this section, I'm going to be using this equation that we had last chapter, which is the amount of heat is equal to mass times the specific heat times the temperature change. And the specific heat for ice is different than the specific heat for water and the specific heat for steam. So the solid, liquid, gas all have different specific heats. And they are back on that table in your chapter 16. This is going to be the change in temperature. So like for here, between 0 and 100, or here it'd be -20 to 0, and this would be the mass of your substance. Now, when they are changing phase, we're going to have a different equation that we're going to use. And the latent heat is the heat that has to be added or removed to convert it from one phase to another. And if we are going from a solid to a liquid, then that's going to be called the heat of fusion, latent heat of fusion. And if we're going from a liquid to a gas, then it's the latent heat of vaporization. And to find that amount of heat, Q is equal to M times L. So M is the mass and L is our latent heat, and that determines the amount of heat that's required. And the latent heat of fusion, as I said, is to go from a solid to a liquid, and the latent heat of vaporization is to go from a liquid to a gas. And on the chart here, they give me, for various materials, what the latent heats of fusion and vaporization are. And this is an F, latent heat of fusion, and this is a V for vaporization. Now, when we're working with phase change problems, not only do we have heat transfers as the temperature increases, but we also have latent heat. So we have to incorporate both. So in this case, I have a 1.1 kilogram block of ice, and it's at -5 degrees Celsius. And I got to figure out how much heat's required to change this ice at -5 into water at 50. So in terms of that chart where I had these different segments, I am here where I'm going to have to figure out first to go from -5 to 0, how much heat is involved. Then I have it at 0, and it's going to be going through a phase change, so here I'm going to have to use that latent heat. Then I'm going to be going from water at 0 to water at 100, right up here. And then eventually I could be changing it over at 100 degrees and heating it up, where I'm changing phase. So in this case, I'm going to change it from -5 to 0. I'm going to have to change phase, and then I'm only going to 50. So I'm going to stop right here. That means I'm going to have 1, 2, 3 segments that I'm going to have to worry about. Okay, so the first segment and the third segment are both the same, and that I'm going to be using my MC delta T. Okay, so I'm going to do the first segment first, and this is going to be my mass, 1.1, times the specific heat of ice. So I'm going to have to go back to that chart and look at the specific heat of ice, and I find that that is 2090. And in that case, my temperature change is from -5 to 0, which is 5 degrees. So I'm going to multiply all those together, and I get 11,495 joules. And that's to find the first segment. Now, to find my second segment, this is changing phase, so I have to use my latent heat. So 1.1, and then I'm going to have to look up the latent heat of fusion for water. And so I went back to that chart, and it's 3.3 times 10 to the 4th. And I multiplied those together, and I got 36,300. And those are joules again. This is Q2. And then I'm going to go to Q3. And Q3 is going to be this section where I'm changing phase again. So M, C, delta T, 1.1 times the specific heat now of my liquid for water, which is 4,190 off my chart. And my temperature change is going from 0 to 50. So it's a temperature change of 50. And when I multiply all those together, I get 230,450 joules. So the total amount of heat that's required is from segment 1, segment 2, and segment 3 all added up. So my total is 1 plus 2 plus 3. 11,495 plus 36,300 plus 230,450. And if I add all those together, I get 2.8 times 10 to the 5th joules is the total amount of energy that it takes. Now in your specific example that you have on your problem, and that's problem 17.58, yours is very much like that, except you don't know the mass, but you know the total heat. And that total heat is going to be section 1, so MC delta T, plus section 2, M times L, plus section 3, MC delta T. That means that you could factor out the mass. So you could have C delta T from the first section, plus L from the second section, and if I factor out the M here, plus C delta T for the third section. And you're going to know the total amount of Q that they give you, the total amount of heat. You're going to know, again, the specific heat for ice and the temperature change. You're going to know the latent heat that's required, the latent heat of fusion, which is going to be this 3.3 times 10 to the 4th. And you're going to know the specific heat of water, and you're going to know the temperature change that you're going to plug in here, depending on how high you want to heat it. And so you'll know all of that stuff that you can add up. You're going to know this, and if you divide, that's going to tell you what your mass is. So that's for 17.58. And that should be the end of chapter 17.